Hello, welcome to lecture 18 of Electrical Circuits 1. In the last lecture we talked about the natural response of first order circuits. I'm going to review that very briefly at the beginning of this lecture because there's some terminology and some concepts there that we'll need when we go on to our main topic today, which is the forced response of first order circuits. So now we're going to have first order circuits, which will consist of one energy storage element, either a capacitor or an inductor, and some resistive elements. But we're going to have a source term. We're going to force these circuits. Specifically, we're going to look at forcing functions which are step inputs. So we'll do general forced response stuff, mathematics, then we'll look specifically at the step response of first order circuits. So we're going to be applying step input functions to these circuits and looking at the response. We'll spend most of today's lecture doing examples of these types of circuit responses. Related educational modules are sections 2.4.4 and 2.4.5. There are a few basic concepts relative to the natural response of first order circuits that we will need to use when we're talking about the forced response of these circuits. First, we have to remember, for a first order circuit, we have one equivalent energy storage element. There is either one equivalent capacitor or one equivalent inductor. Also remember that when we talked about capacitors and inductors, capacitors in series and parallel could be combined to a single equivalent capacitance. Inductors in series and parallel could be combined to a single equivalent inductance. So we have one equivalent energy storage element. For the natural response, we have no sources in our circuit that we are analyzing. Okay? We may have sources which provide an initial condition to us, but when we're analyzing the circuit, those sources have been removed or isolated from the circuit that we're analyzing. So the response that we're calculating is strictly due to the initial energy which is stored in these energy storage elements. There is no external input, there is no energy being supplied from the outside world to this circuit while we're calculating our response. Since we aren't adding energy to this circuit, the circuit response has to decay to zero. We always have some resistance, we always have some energy dissipation, so this initial energy storage has to be dissipated with time. Our response has to go to zero as t goes to infinity. Okay, now we're going to consider the response of electrical circuits which contain sources. We're going to look at the forced response of circuits. And I want to give a quick overview of some of the basic ideas before we get into the details associated with these. First of all, we're going to have sources included with our circuit while we're analyzing the circuit response. Okay, the circuit that we're actually analyzing is going to contain sources. We don't isolate the sources away from the circuit before we start analyzing it. For example, an RC circuit, we might have some voltage source applied to that. We might be interested in the voltage across the capacitor. So we're going to have to analyze this overall circuit, including whatever arbitrary time signal we're putting in as this voltage. Another example might be an RL circuit. We have an energy storage element. We also have some external source, in this case a voltage source, which is applying energy to this system as time goes on. Couple of notes about these. I'm going to be very rigid about this first thing. I'm going to write my governing equations in terms of currents through inductors. So if I have a circuit like this, I'm going to write governing equations in terms of I sub L of t. Or I'm going to write my equations in terms of voltages across capacitors. If I have a capacitive circuit like this one, I'm going to write my equations in terms of V sub C of t. I'm going to do that regardless of whether the capacitor voltage or the inductor current is what I'm actually ultimately interested in. It turns out that if you know the energy as a function of time in all the energy storage elements in your circuit, you can find out anything else about the circuit that you want. So for example, if I'm actually interested in the voltage across the resistor, I can still solve for the current through the inductor. Then this voltage is R times I of t. Okay? I'm always going to use these things as my unknowns unless I just decide to do an example in which I want to do something contrary to this. But in general, this is what I'm going to do. Also, I've shown you circuits that contain a single voltage source and a single resistor with an energy storage element. A single voltage source, a single resistor with an energy storage element. They don't look very general, but they are. If we take advantage of Thevenin's theorem, we can always take a complex circuit and replace it with this type of arrangement. Likewise here. Any linear circuit can be represented as a voltage source in series with a resistance. So we'll use these to conceptualize our solutions. Then when we actually start analyzing specific circuits, they may not actually look like this, but the concepts that we develop in the context of these examples will still apply to those systems. Now let's take a look at the governing equations for the circuits that we saw on the previous slide. So what we'll do is a couple of simple examples. We'll develop a trend from that. From that trend, we'll develop our overall general solution to a forced first-order system. So here's my RC circuit. I have identified an unknown V sub c of t. I'm going to write the governing differential equation for this circuit in terms of V sub c of t. Because I know that the capacitor energy storage is related to the voltage across the capacitor. If I know the energy storage in the energy storage element, I know everything else that I need to know about this circuit. So for this particular circuit, let's define node A. Let's do KCL at A. Okay. So I'll assume that my currents are leaving this node. So the current through the resistor is this voltage, V sub C, minus this voltage, V sub S. So V sub C of t minus V sub S of t over R is that current, plus this current through the capacitor. Notice that my positive current direction agrees with my voltage polarity according to the passive sign convention. This I sub C is equal to C dVc by dt. So this current is C dVc by dt. That has to sum to 0. Now let's divide both sides by C. That gives me dVc by dt plus this V sub C is a 1 over RC times V sub C. I can take this V sub S over to the other side and exchange that negative sign for a positive. This becomes a 1 over RC times V sub S of t. Okay. Remember, for an RC circuit, R times C is the time constant. This guy here is still our 1 over tau term, except that with our natural response, okay, the unforced circuit, we had a 0 on this side. We now have a forcing function. Okay, this is the big difference between what we're doing now and what we were doing in the last lecture. Now let's go take a look at the corresponding circuit for an RL combination. Okay, let's take a look at this RL circuit with a voltage source applied to it. Again, I'm going to write my governing equation in terms of the current through the inductor. Okay, once I find the current through the inductor, I will be able to find out anything else that I need to know about this circuit. I think what I'll do is KVL around this loop. So if I start down here, I get a minus V sub S of t. KCL at this node, since the resistor and inductor are in series, tells me that the current through the resistor is the I sub L of t that I'm writing as my unknown. So this voltage is a plus R times I sub L of t, plus this V sub L is L dIL by dt. that sums to 0. So dividing through by L, I get a dIL by dt plus R over L times I sub L is equal to, if I take this over to the right-hand side and divide by L, I get a 1 over L V sub S of t. This is my governing equation. Again, this term here is still my 1 over tau that multiplied my unknown term with the natural response. The difference is now this forcing function. Okay, when we were doing natural response, this junk here was equal to 0. Now it's equal to some arbitrary function of time. We don't know what Vs of t is yet. Okay, let's go to the next slide and summarize some of these results and then try to generalize them to an arbitrary system. Okay, now let's summarize our previous results for RC and RL circuits and look for some trends or patterns in the result. For my forced RC circuit, I had the derivative of the capacitor voltage with respect to time plus 1 over RC times the capacitor voltage is equal to some forcing function. RC was my time constant when I was looking at the natural response of RC circuits. If I make that substitution here, I end up with dVc dt plus 1 over tau times V sub c is equal to some forcing function. Let's take a look at RL circuits. The forced RL circuit response is dIL dt plus R over L times the inductor current is equal to some forcing function. R over L is 1 over my time constant for RL circuits. If I make that substitution, I end up with dIL dt plus 1 over tau times I sub L is equal to some forcing function. These two equations are virtually identical with the exception of a change of variables and a slight difference in the forcing function. However, if I think of this as an arbitrary time function, that doesn't worry me too much. So let's take that fact and develop some general relationships for first-order systems. Okay, let's look at a general first-order system. From a block diagram standpoint, I've got some system. Its output is y of t. Okay, for an RC circuit, this might be the capacitor voltage. For an RL circuit, this might be the inductor current. So my output is y of t. My input is some general function u of t. I also have the possibility of having some initial condition. So the output at time t equals 0 is some number y sub 0. Now, back when I introduced first-order systems a couple of lectures ago, I provided a general governing differential equation for a first-order system. I used an arbitrary constant, a1, times the derivative of the output with respect to time, plus a0 times the output itself is equal to some input function. This is a general differential equation that will govern this system. I can rewrite that by dividing through by a1. Okay? So I can rewrite this as dy dt plus a0 over a1 times y of t is 1 over a1 times u of t. This was always 1 over tau when I normalized the leading term on my derivative for RL and RC circuits. Therefore, I can substitute 1 over tau here, and I can write this general governing differential equation as dy dt plus 1 over tau times y of t is equal to 1 over a1 times u of t. Okay, this is the governing differential equation that controls both RL and RC forced circuits. Before we talk about step responses of first-order circuits, I want to do a couple of examples of determining input-output differential equations for active first-order circuits. This is our first example. It's an active circuit. It has an operational amplifier. I have one energy storage element, the capacitor. I have a couple of resistors. Therefore, this is going to look like a first-order circuit. I'm going to expect it to be governed by a first-order differential equation, which is going to relate the output V out to the input Vm. Now, in order to analyze this circuit, I'm going to define a voltage V sub c across the capacitor. Now I'm going to apply my operational amplifier rules. If this voltage difference is V sub C and I assume that this is 0 volts, then this voltage here is V sub C. The operational amplifier says there can be no voltage difference between the input nodes. That means that this voltage here is V sub C. Now, my operational amplifier rules also state that there is no current into the input nodes, so there's no current here. That means there's no current through the resistor and no voltage drop across the resistor. Therefore, V out is equal to V sub C. Okay. Now, I'm going to apply KCL at this input node. So the current going through this resistor, which is going to be Vin minus V sub C, has to be equal to the current through the capacitor, I sub C, which is just C times dVC by dt. So Vn minus Vc over R is equal to C times dVC by dt. V out is just equal to V sub C. If I divide through by RC, I get V in over RC is equal to dVC by dt, but VC is just V out, plus 1 over RC times V sub C, which is just V out. There's my first order differential equation governing this circuit. This differential equation is identical to the differential equation governing the passive RC circuit that we did earlier. So the input-output relationship for this one is identical to the previous one. The difference is that this is an active circuit. Okay? The reason you might want to use an active circuit is that any power requirements at the output are going to be provided by the operational amplifier itself. So when you load this circuit, it will be less sensitive to loading effects. Those effects will be looked at more carefully when we do a lab assignment associated with active first-order circuits. Our second active circuit example is this one. We want to determine the differential equation governing the output voltage relative to the input voltage for this circuit. Remember that we don't have a specified input voltage as a function of time. This is any arbitrary signal at this stage. We haven't started considering specific signals. As usual, we're going to apply the op-amp rules. If this is 0 volts down here, then the operational amplifier is keeping these voltages the same. The voltage at this node is 0 volts. Also, there is no current into the input nodes of the operational amplifier. This current is 0. If we do KCL at this input node, the current across the resistor is Vn minus 0 over R. That has to be equal to the current through this capacitor. By the voltage current characteristics for the capacitor, I sub C is C times dVC by dt, where V sub C is this voltage difference with my positive node being at the node that the current is assumed to go into. Vc is positive here relative to here. V out is positive here relative to ground. V out is just the negative of V sub C. Now if we substitute this, dV out by dt is equal to minus 1 over RC times V in. Let's integrate both of these with respect to time. So V out of t is equal to the integral from 0 to t of minus 1 over RC times V in integrated with respect to time. What this circuit is doing is its output is the integral of the input. So this circuit is an integrator. Okay? It inverts because of this negative sign, but ultimately it's integrating the input. As I said previously, operational amplifier circuits tend to do mathematical operations. Here's an example of a mathematical operation that's performed by a circuit which has an energy storage element. All of my previous derivations and results were for a completely general forcing function. Okay, on the previous slide, U of t was my input to my system. I didn't know what function that corresponded to. It was a completely arbitrary function of time. In general, in this class, we are not going to be concerned with arbitrary inputs to our circuits. We'll have two primary types of inputs we will be concerned with. The first of these is a step input to our circuit. We'll be determining the step response. Okay, so now start thinking in terms of a very specific input. Any results that we derive for this input is only appropriate for that input. If you use a different input forcing function, you cannot in general take advantage of these, except that when we look at different inputs, we may invoke this stuff to try to place those inputs in context with the behavior that we're seeing. So, previously we were talking about an arbitrary input U of t. Now we are going to be concerned with specific inputs. And overall in this course there are two that we will be dealing with. The first of which, as I mentioned, were step inputs. U of t is equal to U sub 0 of t times, in general, some number. The other type of input that we're going to spend a lot of time with in this class are sinusoidal inputs. Now, in order to understand step inputs, we need to take advantage of our knowledge about the natural response of systems. Subsequently, when we're talking about sinusoidal inputs, we'll generally take advantage of what we learned about the response of circuits to step inputs. So we're going to defer talking about sinusoidal inputs for a while. We'll just talk about step inputs for now. So we'll see sinusoids later. We'll spend a lot of time with them later in the class. We won't deal with them now. Keep your mind fixed on the idea that we're only applying steps to these circuits. Okay, so on the previous block diagram for our general first order system, our output is still y of t. We can still have an initial condition y sub 0 on the output. Now we're going to get specific about what our input is. Before we had a general input function U of t, now we're claiming that that input is going to be some number a times a unit step function U sub 0 of t. So this input's going to be 0 for times before t equals 0, and it's going to be a for times after t equals 0. A way to implement this from the standpoint of an electrical circuit is with the following circuit. If I have a constant voltage source, which has a voltage of A volts across it, isolated from my system by a switch, and I close this switch at t equals 0, my input, U of t, to this RC circuit is 0 for times less than 0, and it goes up to A for times greater than 0. Okay? So this is how to implement this type of input. If we restrict our attention to step inputs, our governing general differential equation looks like dy dt plus 1 over tau y of t. We had a 1 over a1 times our input, which is now a times u0 of t. Okay, this will be our baseline for a little while now. Okay, now I want to refresh our memory about some of the basics of system responses relative to solving the overall differential equations that govern the system. This information was presented a couple of lectures ago, but I want to bring it up here again so that it's fresh in our mind when I use it now. When we solve the previous differential equation that we had, y of t will be the combination of a homogeneous solution, y sub h of t, plus a particular solution, y sub p of t. Okay? Y sub h of t is the homogeneous solution. That's the solution when I have no forcing function. Okay? Remember a couple of important things about that solution. It is just due to the system's response to initial conditions. Since our systems will always have to dissipate energy, this guy will go to 0 as t goes to infinity. This is the solution that we were determining when we looked at the system's natural response. The particular solution, y sub p of t, is due to the actual forcing function that's applied to the system. Okay? One important thing you have to remember about y sub p of t is that the form of y sub p of t has to be the same as the form of u of t. If u of t is a constant, y sub p of t is a constant. If u is a sinusoid, y sub p of t has to be a sinusoid. Since the homogeneous solution goes to 0 as t goes to infinity, okay, if I let this guy go to infinity, y of t has to be y sub p of t as t goes to infinity. Okay? These facts are going to help us solve the previous differential equation and determine what the overall y of t is. Okay, let's take a look at the homogeneous solution for a first-order system. Now, this stuff we've already done. Remember, we did natural responses of RL and RC circuits. This is the same thing. I'm just going to present it in a little bit more general terms. The approach that I'm going to take to determine the general homogeneous solution of our differential equation is similar to the second approach that I used for the natural response of an RL circuit. I said that it is okay to go ahead and guess the solution to a differential equation. So here we're going to guess that the homogeneous solution, y sub h of t, is equal to some constant k1 times e to the st. Okay, now if I plug this solution into my differential equation, I can solve for k1 and s to satisfy the differential equation. So I'm going to take this solution and substitute it into the homogeneous differential equation. I'm going to remove my forcing function. Remember, y sub h of t is the solution to this differential equation without any input applied to it. So I have dy dt plus 1 over tau times y of t is equal to 0. The derivative of y sub h of t with respect to time is equal to k1 s e to the st. So I have dy dt as k1 s e to the st plus 1 over tau times k1 e to the st. I can divide out the e to the st, and I can divide out the k1. That leads me to the conclusion that s is the negative of 1 over tau. I found one of my unknown constants. Therefore, my homogeneous solution is of the form k1 e to the minus t over tau, which is exactly the kind of thing we were looking at when we were doing natural responses. We determined k1 from the initial conditions. Now let's take a look at the particular solution. Okay, the particular solution to our differential equation is going to depend upon the specific input function that we apply to this. At the moment, we are applying a step function. Keep that in mind. A couple of things to remember about the particular solution. Number one, it has to satisfy the original differential equation as t goes to infinity. Remember, y sub h of t goes to 0 as t goes to infinity, so y of t becomes y sub p of t as t goes to infinity. Also, my particular solution has to have the same form as the forcing function. So for our particular system, I can make a few statements as t goes to infinity about the particular solution. U of t, my input, is just a times u0 of t. u0 of t is 1 for any time greater than 0, so u of t is just a as t goes to infinity. So my input function is a constant if My solution has to have the same form as the input. That means that my particular solution is also a constant as t goes to infinity. There is also a derivative of y sub p with respect to time in my solution. If y sub p is a constant, the derivative of y sub p with respect to time is 0. Okay. Now let's take these guys here, use them in my governing differential equation, and figure out what y sub p of t is. Okay, continuing my derivation of the particular solution for the step response of a first-order system. As t goes to infinity, from the previous slide, we saw that the original differential equation has to become dy p dt. Remember, y of t becomes just the particular solution as t goes to infinity, plus 1 over tau times y sub p is equal to a. The input is just a times 1 for large times. We said that dy p dt is 0 as t goes to infinity because this guy is a constant. Therefore, if I solve for y sub p, multiplying both sides by tau, I find that y sub p of t is just a times tau. Okay? I'm not generally interested in these guys individually. What I can do is just claim that tau is a number, a is a number, therefore y sub p of t is some constant which I'll name k2. Okay, let's put the previous pieces together to determine the form of the overall first-order system step response. We said that the output y of t is the superposition of the homogeneous solution and the particular solution. We also claimed that y sub h of t, the homogeneous solution, is some constant k1 times e to the minus t over tau, and that y sub p of t is some constant k2. Therefore, this is the overall form of our solution for a step response of a first-order system. We can determine k1 and k2 from initial conditions. Remember, when we were doing natural responses, we determined k1 from the initial conditions. We have two unknowns now, however, k1 and k2, so we need to not only use the initial conditions, but we need to determine something about the steady state or the final value that the response goes to as t goes to infinity. So we'll have two pieces of information that we can use to determine the two unknowns k1 and k2. Tau, as always, is a property of the circuit itself. Okay, now let's use our previous results to do some examples to determine the response of first-order circuits to step functions. Okay, our first example is that I have a switched RC circuit. Okay, I want to find the voltage across the capacitor as a function of time for times greater than 0, which are times after this switch closes. My input here becomes a step input. So u of t, okay, if I look at these terminals, my input function is 0 for times less than 0. After I close this switch, my input is 10 volts, so u of t is 10 times u0 of t. I am actually looking at a step response. I can use the information that I've developed earlier in this lecture. Let's also take a look at the initial conditions for this circuit. Initially, I'm going to claim that this switch has been open for a long time. If there ever was any energy stored in this capacitor, it would have been dissipated through this resistor. So I'm going to say that any energy in here is gone before I close this switch. So V sub C at t equals 0 minus is equal to 0. Okay? Another way to state this is that the circuit is initially what is called relaxed. Okay? I'm going to claim that relaxed terminology means that any energy storage element in this circuit doesn't have any energy stored in it initially. Now, before I close this switch, my voltage across the capacitor is 0. I cannot change the voltage across a capacitor suddenly without applying infinite power. Therefore, my initial condition, V sub c at t equals 0 plus, is also 0. So I've done two things up front. I've identified this as a step input. I know that I'm calculating a step response. Therefore, I know that from the previous slide, I can use that form of solution for Vc of t. I've also determined the initial condition on the system. On the next slide, I'll go through and determine the governing differential equation for this circuit. Now for this circuit, I'm interested in the capacitor voltage as a function of time after the switch closes. Therefore, the differential equation that I'm interested in for this circuit has this switch in a closed position. Okay, so I'm going to look at this circuit to determine the differential equation governing V sub c of t. I can do KCL at this node. Then current going into this node is equal to the current coming out of that node. So the current coming into this node is 10 volts minus the voltage here, which is just V sub c, over 100 ohms. That is equal to the current through this 200 ohm resistor, which is just the voltage over the resistance. So it's V sub c of t over 200 ohms, plus the current through the capacitor. This current, I sub c, is c dVc by dt, which is equal to 1 millifarad, or 1 times 10 to the minus third, times dVc by dt. There is my governing differential equation. I'm going to want to rearrange that so that I can identify tau. If I multiply this through by 1,000, I get 100 volts minus 10 V sub c is equal to 1,000 divided by 200 is 5 V sub c plus dVc by dt. Grouping terms, I get dVc by dt plus 15 V sub c is equal to 100. Okay, that's the form that I want this to be in to identify tau. I have a 1 multiplying the derivative term. This guy here is 1 over tau is 15. Okay. So let's go to the next slide, look at the overall form of the solution, and find the remaining unknown constants from the initial and the final conditions. Now the solution to our step response is going to contain two unknown constants, K1 and K2. We're going to use the initial and the final conditions on this circuit to determine these two constants. We'll get what is essentially two equations and two unknowns. Now on the last slide, we determined that the governing differential equation was dVc dt plus 15 V sub c is equal to 100. Therefore, using our results for a general first-order system step response, the form of the solution of this differential equation is going to be V sub c of t is some unknown constant k1 times e to the minus t over tau. This is 1 over tau, so this number comes down here with a negative sign in front of it, plus another unknown constant k2. These two constants are going to be determined from initial and final conditions on the circuit. My initial condition has already been determined as V sub c at t equals 0 plus is equal to 0 volts. This must be true for this equation. So V sub c of t is 0 is k1 times e to the 0. E to the 0 is 1, so this just becomes k1 plus k2. One equation is k1 plus k2 is equal to 0. So I have one equation and two unknowns. I need another equation. I can determine my other equation from the final conditions on this circuit. So let's take a look at the circuit as t goes to infinity. Now we're applying a constant input to this circuit. We also know that the natural solution, or the homogeneous solution, is going to die out with time. So the particular solution, which has the same form as the input, is going to be a constant. So as t goes to infinity, my voltage across my capacitor is going to become a constant value. Remember, one of the properties of capacitors was that everything is constant. The capacitor behaves like an open circuit. Therefore, we can redraw this circuit with the capacitor replaced as an open circuit. So we have a 10-volt source. There was a 100 ohm resistor here. There was a 200 ohm resistor here. And then the capacitor will become an open circuit, and this is V sub c of t as t goes to infinity. This now, since there's no current through the capacitor, just looks like a voltage divider. So the voltage across the 200 ohm resistor is just 2/3 of the 10-volt source. So this is 6.67 volts. Okay? So we know the voltage as time goes to infinity. We can now use that to write another equation. So my final condition, as t goes to infinity, this equation here, V sub c as t goes to infinity, is equal to this number, 6.67. That is equal to k1 e to the minus infinity. E to the minus infinity is 0, so I have 0 times k1 plus k2. So my second equation is k2 is equal to 6.67. Since k1 plus k2 is equal to 0, that means k1 is equal to minus 6.67 volts. And my overall solution is V sub c of t is equal to k1, or minus 6.67 e to the minus 15t, plus k2, which is 6.67. I can pull out the 6.67, so V sub c of t is equal to 6.67 times 1 minus e to the minus 15t for times greater than 0. And in fact, if I graph this, I get a response that looks something like this. V sub c of t as a function of time starts out at 0. It comes up to a final value, which is 6.67 volts. And it has a time constant. Tau is 1 over 15 seconds. Okay, so a quick sketch of the response looks like that. Now, there have been a lot of steps that we've done to get to this stage. We would really like to check our results. On the next slide, I'll go back and take a look at verifying that I've got the right time constant and make sure that we're doing things correctly. Okay, I want to make sure that I didn't make a mistake when I was deriving my overall differential equation. My differential equation gave me the time constant tau. Okay? I can check the time constant directly from the circuit itself. For an RC circuit, which this is, tau is equal to the product of the resistance and the capacitance. This resistance is actually still the equivalent resistance seen by the capacitor. Okay, remember when we did natural response, we could determine the tau, or the time constant, by open circuiting the capacitor terminals, looking into that, and calculating an equivalent resistance. That is still true. Essentially what we're doing is using Thevenin's theorem to see the resistance that's seen by the capacitor. Let's do the same trick here. We're going to open up these terminals, kill the sources in here, the way we did with Thevenin's theorem, and look at the equivalent resistance. This is a voltage source. When I kill that, it will short. I have a 100 ohm resistor here. I have a 200 ohm resistor here. And I'm looking into these terminals to find the equivalent resistance. Since there's no voltage difference here, these two resistors are in parallel. So Req, so a parallel combination of two resistors is the product of the resistances, 100 times 200, over the sum of the resistances, 100 plus 200. So I can factor out a 200 there, and I get 200 over 3, or Req is about 66.7 ohms. Now I can determine tau is equal to R times C, so 66.7 times 1 times 10 to the minus third is 0.067 seconds. That is the same as 1 over 15 seconds. We verified that the time constant that we got previously is correct. This concludes lecture 18. In this lecture, we covered rather a lot of territory. We looked at the general forced response of first-order circuits. We then specifically narrowed our attention to the step response of first-order circuits. We did an example of determining the step response of an RC circuit. So we've got the groundwork laid. Now in the next lecture, we're just going to do more examples of step responses of first-order circuits so that we can see various ways of approaching these problems and get some practice doing these types of problems before we move on to second-order circuits.